Okay, today I want to start the lecture by doing some example of graphing problems. These are appearing at exercises in 1.6. We talked about transformations of trig functions. Transformations that we talked about consisted of reflections. We had shifting, and we had scaling. Reflection means you're taking mirror image of something in X or Y axis. Shifting means moving the picture to the left or right, up or down. Scaling means you are shrinking it or stretching it in either X or Y direction. We had a variety of comments about the situation. When you have many of these things appearing in one problem, it can become kind of overwhelming by keeping track of all the movements. One challenge was that in certain circumstances, the order in which you carry these kind of movements is going to affect your final picture, and so you have to be careful how you are doing it. One general help or tip was that if two movements are one in X direction, the other one in a Y direction, you can interchange the order in which you do them, but other than that, the order is important. Just to start with something that doesn't overwhelm us with all sorts of movements all at the same time, let's start with this is problem 15. Says y is equal to 1/3 of sine of x minus 4. In general, we are aiming at handling a situation where you have all of these things thrown in. So you have a number up front of a function and a number later on added or subtracted. Input of the function also has a linear expression in it. This one doesn't have all those components. Here I just have an x, so I don't have a b or c. B is 1, c is 0, so I don't have any horizontal things to worry about. But I have two vertical ones. A and D components are here. How do we go about handling this problem? First, of course, we need to know the very basic function itself. We have sine function. We decide from the outset to go degrees or radians. Here doesn't make any difference which one you do. So if it is gone with degrees, 0, pi, and 2 pi, that makes our fundamental cycle of this function. So I have some function kind of looking like this perhaps. It has a height of 1, comes to minus 1. Period is 2 pi. The amplitude of it is 1, and so on. Now, I have one factor here, which is 1/3. What does 1/3 do? 1/3 shrinks your function vertically, so the height of it, instead of being 1, is going to be shrunk to 1/3. So the height comes to 1/3, and the low point also comes to minus 1/3. So on the new function, this portion of it is going to be having something like this. So if we take that number, scale vertically by that number, scale by 1/3 in y direction. So it kind of shrinks here. Then we affect this one, that we shift the function in which direction. This minus 4 is going to shift the function vertically. It's going to lower the function. So minus 4 is going to bring the function to, here's minus 2, minus 3, minus 4. If you wish, you can take the midline bring the midline to -4 and wrap your function around that. So your function is going to come up. So let's write, this is the graph of y is equal to a third of sine of x -4. First, what we did was to shrink it. With respect to the vertical movements, it's unlikely that you go wrong. It's kind of hard to miss the steps because you have things to help you. That you realize the amplitude is 1/3, and you realize that midline is at -4. So in your mind, that prevents you from making any kind of order errors. If you could even think that here's my midline and I'm going to wrap around it a sine curve with a amplitude of 1/3, everything is safe and sound over there.
So whenever there's a number outside of the parentheses, we can assume that is our midline?
I'll have to be careful how to answer this. Outside of a parentheses, this is outside and that is outside, so the number that's added or subtracted, yeah. So if the problem was simple like this, y is equal to a sine of x plus d, you can break the problem in several steps. Step 1, amplitude is that number. Step 2, so scale, I'm going to explain shortly why I'm putting in absolute value. Some problems you say that number is negative. So for example, I could have had y is equal to -2 sine of x plus 3. What are the steps? Let's go explain these steps here. First, I draw my basic function. Here's my basic function. Then I scale it by that factor, 2. So by factor of 2, scaling by 2, that is 2 sine x. So the green one is just sine x. Now, so what's the influence of -2? Yeah, it flips it upside down. So -2 sine x becomes like this, -2 sine x. So here we say, step 2, if a is negative, flip upside down. Or more properly spoken, reflect in x-axis. Yeah, this is the x-axis. You put a mirror on the x-axis and reflect in the x-axis. The movement is in the y direction, but the reflection is in the x-axis, meaning the mirror is sitting there. Step 3, move midline to D. So that is essentially a shift by D in vertical direction. So when you say shift by D, if D happens to be positive, you go up. If D happens to be negative, you go down. So this type of functions are essentially the simplest ones to draw. Always you have a fallback position. The very rudimentary way is to point plotting, sitting there patiently, putting numbers in the calculator, getting it out, and plotting it. That you can graph anything in that fashion. Problems, of course, it takes time. We have default position number 2. for this trig functions, we said there are specific handle points, highs and lows, end point of the periods, crossing points, and all of that. You can backtrack all of those and figure out where they go. That also gives you another way of graphing it. Here in the language of shifting, scaling, translations, reflection and such, we are explaining how to do this graph. The ideas we are expressing also applicable to other functions. Now let's go ahead and do something a little bit more involved. And that would be such as,
Are you in 1.6?
you are 1.6, yes. Question?
Look at number 26.
26. Okay, let's we do 26 next. Let me choose something that just concentrates on next two items, and I don't see. Okay, instead of 26, let me do 16, and then I come to your 26. Y is equal to cosine of 1/2 of x plus pi over 2. So this falls in the category of handling functions where only the interior is being changed. Okay, the previous one we had this type. A is out here and B is out here. This is only the interior. Bx plus c is showing up. Of course, our long-term plan is to go, hopefully, to throw in everything in the kitchen sink. We have A and a D and a B and a C and everything. So we have all sorts of movements happening in all sorts of directions. But now let's just do this. Bx plus c. Okay, the book's advice on this thing to make the language similar to what we have been doing is to factor b. So this is going to appear as, maybe the book writes it in a different style. Let me write exactly the same way as the book does so that you don't get confused. I guess the book uses bx minus c. Yes. It doesn't matter so long as you know what is intended. The reason for this peculiar switch is what I mentioned, that there is really a way of handling all of these movements with a single recipe if you are comfortable with the notion of inverse functions. If not, then we have to go through, if it looks like this, do it this way. If it looks like that, do it that way. So you're paying a price here by not adopting more general language. So following that recipe, we factor our b. What's our b? Multiple of x. So I'm going to have 1/2 x. What's going to be left after I factor 1/2? Pi. So we are going to have two steps to go through. One is scaling. So we say scale. The graph of y equal to the grandfather graph is cosine of x by a factor of what? How is it going to stretch or is it going to shrink in the horizontal direction? By a factor of 2. So in other words, to say it explicitly, stretch by a factor of 2 in x direction So let's do that step. We take the graph of cosine. You have to remember that graph, so we try to do a reasonable cosine. We draw at least one cycle of it. This is implicit here that when there is a pi, the assumption is that we are doing everything in radians. It doesn't have to be like that, but that is the convention. So my original settings were 0 pi over 2, 0 pi over 2 pi, three pi over 2, and 2 pi. So if I stretch it by a factor of 2, what happens to this point? When you stretch it, imagine a left point of the slinky being held by somebody, or you just nailed it to the wall. So items that are glued to the y-axis, they are not going to move. Same way that in this case, when we were taking this green picture of sine of x, I wanted to double it. Every point that was glued to the x-axis, they are not going to stretch or anything. They are going to stay put. So when we are doing horizontal movements, when it comes to scaling, if you are on the y-axis, your x is 0. If you double it, this is still 0. Next point to track, easy point to track, is pi over 2. Where is that going to go? It's going to go to pi. And the point that was pi, so let's see. Where would this minimum point going to go? It's going to go here, at 2 pi. So next point to consider is this crossing point. It was 3 pi over 2, so now it's going to be, let's continue this thing. So I have 5 pi over 2, 3 pi, 7 pi over 2, say 4 pi. So 3 pi over 2, stretching it by a factor of 2, next important point is this high point. The high point is going to get stretched, come all the way to what? 4 pi. So what I have so far is y is equal to cosine of x over 2. So when you have x over 2, your x has to go as far as 4 pi for the argument to go as far as one fundamental cycle. Next is the issue of the phase shift. Our phase shift in this problem is, so let's keep track of period. What's the period of my new function? 4 pi. So period is equal to, in general, 2 pi over whatever coefficient you had here, 2 pi over b. In this case, we have 2 pi, or b happens to be a half, so makes 4 pi. So double check in with various concepts that you have to make sure that your period comes out right. After you divide by 2, it stretches, your period becomes 4 pi. Next issue is how much do I shift it and in which direction? So we have a shift. When we write it in this style, that shows you the shift. If it is positive, you go to the left. If it is negative, you go to the right. So shift left. So we have a phase shift. Which is if you want to think about it, it's pi over 2 divided by 1/2. The negative of that is your phase shift. Negative C over B, negative of pi over 2. So I'm incorporating the direction into my phase shift. In general, they just say phase shift by pi to the left in either way. So move to the left by pi. So where does my starting point go to? Let's see, put it here. How about my crossing point? Comes to the origin. So let's and then next important point is this low point that's going to come here. Next important point is this crossing point. 3 pi is going to come to 2 pi. Next important point is this high point from 4 pi is going to come back up to 3 pi. So this is the graph of your y is equal to cosine of either this style or that style, cosine of x over 2 Now if you had done backtracking of important points, you would have found out right from the first start that this point is going to come here, this point is going to come here, and so on. So that was problem 16. Now let's go ahead. Let me try to get some headway into our lecture for today. You make sure that you practice these two aspects. You wanted 26 also? Let me see. 26. Can we postpone that for tomorrow? Okay. Let's put 26 so that I squeeze. I finished section 2.1 and we want to go to 2.2. Yeah, hopefully we get to the somewhere to midpoint of our syllabus. That would be good. Now, so section 2 of our lecture, we are gonna. So again, we are gonna do one graphing problem every day until Friday, and gradually add up more and more flavor to the graphing questions. So the combination of the two problems that we have done was something like Sarajin was asking for. That problem 26 has everything in the x direction, everything in y direction, and so on. But let's split the job right now. So from section 2.1, we are talking about sum and difference formulas. Today I will just list them and go through some practice problems with these. And, tomorrow I probably give you the proofs. Okay, the grandfather of these sum and difference problems is the following identity. What is the cosine of an angle minus another angle? So x and y are two angles, or alpha and beta are two angles. We want to find the cosine of the difference of these two. Now, using the Pythagorean identity that we talked about, or Pythagorean formula for the right triangle, we can show that this turns out to be this peculiar expression. Some of you might recognize it. This is cosine of x times cosine of y, and what else? Anybody remembers? Plus sine of x times sine of y. We haven't had any identity that complicated yet. Where do all these things come from? They are really related to Pythagorean theorem for a right triangle, and these expressions are really related to what you see in algebra problems when you have sum or difference of two quantities squared. You see squares, but you also see something else. What's that other thing? Minus product of one item and the other item. All I'm trying to say is that the appearance of these peculiar expressions, this multiplication, has something to do with that, and the identity itself has something to do with the Pythagorean theorem. Okay, this is cosine of difference of two angles. Suppose we pick an example. Suppose I want to ask you to find cosine of, say, 15 degrees exactly. Well, of course, approximately you can type 15 degrees on your calculator, press the cosine button, and there comes the value of it. More up-to-date calculators, they actually give you the exact value, but we want to find it, see what's the origin of one of such formulas. So remember 15 degrees, can we make it out of angles that we are familiar with? Yeah, 45 minus 30, or 60 minus 45. So we start with the angles that we know, manipulate them until we get the angles, that angle that we want. This is, either of these things would be fine. So I pick one of these things. For example, I say, what is cosine of 60 minus 45? That is what cosine of 15 degrees is. Okay, according to this formula, which we didn't prove yet, but let's take it as our starting point. This has to be cosine of the first times cosine of the second minus, plus sine of the first times sine of the second. Now everything is going to depend on our memory on these famous angles. Let's just quickly refresh our memories. There were two triangles that you needed to remember to be quick with these type of questions. With respect to 30, 60, our triangle was 2, 1, and the other side was what? Square root of 3. Or with 45 degree, our triangle, the easiest one to remember perhaps, 1 and 1 and radical 2. If we know these things, cosine of 60, ratio adjacent to hypotenuse, what is that? So I did all the work, so you have to be quick on this. Cosine of 60 is ratio adjacent to hypotenuse. That's just 1/2. Cosine of 45, ratio of adjacent to hypotenuse, 1 over radical 2. Let me write it here. Cosine of 60 is 1 over 2. Cosine of 45, 1 over radical 2. We had also another way of doing this thing. By rationalizing, what do we get? Either of them is fine. So I can write radical 2 over 2, or 1 over radical 2, plus sine of 60. What is sine of 60? Sine of 60, square root of 3 over 2. So I write that. Sine of 45, again, opposite to hypotenuse, just like this. Sine of 45, same as cosine of 45. It's radical 2 over 2. Okay, by keeping all denominators whole numbers, I made my life a little bit easier, because now the common denominator is just 4. 1 times radical 2. Radical 3 times radical 2. What is that? You need your knowledge of college algebra to do this. What do we get? Radical what is radical A times radical B. Another way of writing it, so long as A, B, both of them are not negative, this is correct. This becomes radical 6. So what we got out of all of this calculation is a very neat, surprising answer, that 15 degrees falls in a category of angles for which we can have an exact expression of what is its sine or cosine or tangent or anything else. So to the arsenal of the famous angles that we know exactly what's the deal with them, we are adding one more. Not only 30, 60, and 45, but 15 also falls in that category. Now I use 60 and 45, you could have used 45 and 30, you'll get the same answer. Sometimes you might be wondering, well, what if I were adding these two? I would be targeting cosine of 105. But let's go first figure out the identity. Before I go there, let me put this thing in some attention grabbing things. This is one formula we need to now. Next, so how about cosine of x plus y? Now you have two options. One is just learn something all over again, memorize something new, or try to extract it from what you had. Let me first write it down, something you need to memorize, plus we are going to try to establish a link so that you see that if you know that, you will know this one as well. What do you think is going to look like? Cosine of x, cosine of y, minus sine of x, sine of y. Why would we suspect the answer should be coming with minus? Because I could have written this thing like this, cosine of x minus, how can I write plus y? Plus y is same as minus what quantity? Minus y. So I can trick the problem, making it look like a subtraction. Then I can take this problem and say, okay, you told me if I had difference of two quantities, go and do that. Now, one of my quantity is just same x as before. The second quantity I'm subtracting is minus y. It is really minus y I want to use. So all I have to do is to replace my y's here with minus y. Let's see what happens. Cosine of x, cosine of minus y. So I'm copying this, except instead of y, I'm putting minus y. Plus sine of x, sine of minus y. Now it's time to make use of those negative angle identities. Do you remember how they look like? What was cosine of minus theta? That is same as cosine theta. What about sine? Negative. That meant cosine is an even function. It splits evenly across the y-axis. This meant the sine is an odd function. It has symmetry with respect to the origin. Anyway, what we use it for here is that cosine of minus y is exactly the same as cosine of y. That is this identity. This identity I come here, says sine of negative, negative survives, comes outside. So sine of negative y, I will write it sine of x times minus sine of y. That minus comes out. Now I bring it all up front. It becomes minus sine of x, sine of y. So this is our identity number 2. Cosine of the sum of two angles let's practice something here. Suppose I ask you find cosine of 75 degrees. Here I scratch my head, say, can I make my 75 in terms of angles I am familiar with? Suppose we're just starting and all we know is 30, 60, 45. So how can I write this? This is same as 45 plus 30. Is that right? So I can write like this. Cosine of 75 is same as cosine of 45 plus 30. And that, according to this formula, is just cosine of 45, cosine of 30, minus sine of 45, sine of 30. That we just saw. Radical 2 over 2. What is cosine of 30? Cosine of 30 adjacent to hypotenuse, radical 3 over 2. Sine of 45, we just saw that. Sine of 30, we just, well, sine of 30. Opposite, 2 hypotenuse, this 1/2. We clean up as last time. Radical 6 minus radical 2 over 4. That is cosine of 75.
Dr. Mason,
Yes.
could you back up? Because in the red ink up there, you
Yeah.
went from, right where you have that mark, I understand that step. Cosine of minus y is equal to cosine of y,
Uh-huh.
right? Because it's positive. But to go from the sine portion right there
To this.
out from that step,
From here to here,
next one, where you
that minus comes out. Is that where the,
I know how that is. That's equal to the one above. But to take the next step, the one you have boxed, and to say that plus sine x is now equal to minus sine x.
okay, no, this is, I'm multiplying sine x with minus sine y. Plus, then I say plus times minus, I put that minus up front. It's like saying plus 2 times minus 3 is same as minus 2 times 3. So that minus is just moved here.
Thank you.
Okay, so let's take a 2-minute break here so that we refresh and make sure our file sizes are also small. Okay, so let's take 2 minutes and we'll come back.